Does size really matter? I'm not sure what you're thinking about, but if it's regarding logic devices, the answer is absolutely yes. In fact, most innovations in logic have not been so much in the silicon, but in the packaging that holds the silicon. In this lesson, we're going to look at the huge varieties of logic packages and how to select the right one for your application. This is the DIP, the dual inline package. In the beginning days of logic devices, this was the standard. Each pin required that a hole be drilled in the circuit board. Now they work great, but as the devices got more and more complex, the package got larger and larger as well until they were affectionately referred to as aircraft carriers. Meanwhile, products were getting smaller and smaller, and these packages, they just didn't fit in the applications anymore. Sure, they still had their places, but the world needed something much more compact instead. The first solution was to get rid of the need for drilling holes, which created the surface mount package. Instead of going through the board, the leads were bent out and connected to the surface of the board with little gull wings. Now these are known as the SO, or the small outline package. And since there was no longer a need to drill tiny holes close together on the circuit board, the distance between the pins, known as the pitch, was reduced from about 2.54 millimeters on the DIP to 1.27 millimeters with the SO, less than half the size. These packages were much smaller than the DIP, but again, as the pin count went up above 50 pins, even these small packages became too big for many applications. One way to get a lot of connections into a very small space is with tiny balls, like this, the BGA or the ball grid array. Place the balls on a grid with less than 1 millimeter pitch, and you can get 100 contacts into a device that's the size of your fingernail. But BGAs come at a cost, and those balls make for very small attachment points, which can sometimes lead to possible mechanical and electrical issues. So an even better solution is to get rid of the pins and balls completely and go leadless. Now this is called the QFN package, or quad flat pack. No leads. The connection pads are as close as 0.4 millimeters pitch, which is about the smallest that most assembly machines can pick up and place in the first place. You can get a lot of pads on this package, up to 60 pins in some configuration. But the outside of the package is still only a few millimeters on a side. This sort of brings a whole new meaning to the term computer bug, but in a good way, doesn't it? Packages like these big QFNs and BGAs are great for those big 16 and 32-bit logic bus drivers. But frankly, most logic gates have much smaller needs. In fact, most logic packages today don't need more than 10 pins, or even 6 or 8 pins is enough. So imagine if you took a design like a QFN and you shrunk it down to just a couple of pins, and you get something like this. If the top line of packages can be called the big packages, then the lower line are really small packages, as you can see by their nicknames of PicoGate and MicroPack. These package options get smaller and smaller as you move to the right. By reducing the number of pins and reducing the pin pitch, you can get some very tiny packaging solutions. This card shows you an example of big packages on the left column compared to small packages on the right column. And look at the incredible space savings that you get going from, for example, a TSSOP 20 to a DHV QFN 20, or from a TSOP 8 to an Exxon 8, or all the way down to a miniature BGA, this 10-pin WLCSP, from when only the smallest size is absolutely critical. For several generations, NXP has been the world leader in the smallest logic packages. First, there was the GS package at 1 by 1 millimeter with a 0.35 millimeter pitch. Then the GN package at 0.9 by 1 millimeter with 0.3 millimeter pitch. But hey, not sitting on its laurels, NXP then set out to beat itself with an even smaller package, which is called the Diamond package. This is the Diamond package. It's a 5-lead package, which is great for most single logic devices. Power, ground, 2 inputs, and 1 output, that's 5 pins. Now the outside dimensions of this package are 0.8 by 0.8 millimeters. Take out a ruler that you own that's marked with millimeters. Those are the smallest, narrowest lines on the ruler. The Diamond package would fit comfortably between 2 of those lines without even touching either one of them. You see, this is how a device is typically placed and soldered on a board. Here's a small demo board that uses the 74 AUP 1Z04 in the GW or the PicoGate package. It's actually a pretty large package, but it shows the point. Now here's a drawing of a typical PCB board layout from both the top and the side view. To connect this device to the PCB, you need to place solder on the pads of the circuit board, but nowhere else. To do this, you need to use a stencil or a mask so that the solder in the form of a paste like toothpaste will only go onto the printed circuit board contacts. To do this, you carefully place the stencil over the PCB. Then you use a squeegee to rub the solder paste over the holes and onto the PCB below. When you're done, a tiny bit of solder paste is left as a coating on the PCB pads. Now for pin pitches above about 0.35 millimeters, you can use a regular stencil, and its thickness dispenses exactly the right amount of solder onto the PCB. However, below 0.35 millimeter pitch, that glob of solder paste is just too much. When you reflow it or when you heat it to its melting point, it will just run all over the place, including between the PCB traces, shorting them out. The solution then is to get a thinner stencil, which is only 80 microns thick, which has smaller pockets for the solder to paste to collect in, and thus deposit less solder on the circuit board in the first place. Simple, right? Yes, a smaller amount of solder paste is deposited, but think how thin 80 micron thick stencil is. For example, the aluminum foil you might find in your kitchen is about 200 microns thick. Needless to say, an 80 micron stencil is very flexible and very fragile and very expensive. The NXP Diamond package may be only 0.8 millimeters on a side, but the pitch, the distance between each pad, is at least 0.5 millimeters because it's on a diagonal. Even more important is the space that this allows between the contacts so the solder doesn't bridge over, all without that expensive step-down mask. It's the tiniest package with the easiest solder pins. So DIP, TSSOP, BGA, QFN, MicroPack, Diamond Pack. Besides just the size, how do you know which package to pick? Here's a couple of hints. Face it, if you can't see the pads hidden under the package, you can't connect to them for test and measure. So in the lab, this can be a real problem. How do you check your circuits if you can't get to the pins in the first place? But out in the field, the lack of accessible pins can actually be an advantage. Your competitor can't easily probe the signals on your board and see what it's doing. And there are also fewer open contacts to be contaminated by water or metal particles and affect your reliability. Now how about strength? Which of these packages holds onto the printed circuit board the strongest for the highest mechanical stress applications? You might think that the package with the most metal in the pins, the leaded Pico gates, would be the strongest. But you'd be wrong. The MicroPack, with its flush pads, actually provides more pull strength if you try to pull the package straight up off the board, or even if you try to shear it off the board from the side. They pass Q100 standards for high vibration automotive applications. You can also see that the BGA, with only tiny balls to hold it onto the printed circuit board, turns out to be one of the weaker packages. Finally, what about price? Obviously, the smallest package with the least materials with the highest volume should have the best chance of being the most cost efficient, because that has a snowball effect as well. The better the price, the more parts are bought, and the more efficient the manufacturing process becomes. The NXP MicroPack is now so popular that literally billions of them are made every year in multiple facilities around the world. This means that you'll never have to worry about picking the wrong package. Packages then, from this to this, and everything in between, there's pretty much a solution for all your logic packaging needs.